This is another video in the series of the numeracy lessons. Today we're going to take a look at something called significant digits or significant figures. So before you actually watch this entire video, I recommend that you watch the 3 videos that are listed on this slide here, because you'll notice in your word handout that you have to define 2 words, and those 2 words are precision and accuracy. And after you watch the 3 videos below, you'll have a good idea as to what precision and accuracy are. You'll be able to define them, and you'll actually also be able to proceed through the rest of this video already knowing the information there. You'll just have to kind of use it as a review. So again, watch 3 videos below for precision and accuracy. Write their definitions down in the Word document that's provided to you, and then continue watching just so you can get more details on what significant figures and significant digits are. So the rest of this PowerPoint is really basically a review for you. So before we go into significant digits or significant figures, we're going to talk about 2 types of numbers: exact numbers and measured numbers. So exact numbers are quantities that you can actually count, and there's no uncertainty to those quantities. So for example, right here there are exactly 3 people. There are exactly 3 people. It wasn't something that was measured. We can see that there's only 3 people in the room, and that's called an exact number. So we're certain of that. There's no uncertainty there. Now, in science and math and other areas of research, there's uncertainty. Whenever you measure something, there's always some degree of uncertainty. There's limited precision when you're measuring. So let's look at an example here. Over here we have a pen that we're trying to measure. And so you'll notice that it's at least 4 centimeters, at least 4.5 centimeters, and even a little bit more than that, 4.6, 4.7 centimeters here. Now let's zoom in. We know it's at least 4.7 centimeters. So between 4.7 and 4.8, maybe it's 4.72, maybe it's 4.73. We don't have those defining lines there to actually tell us if it's 4.72 or 4.73, what's in between. Now, even if we did have lines here, then you'd have to have more lines in between to know exactly is it 4.721, 4.722, 4.723, or so on and so forth. So whenever you measure something, there's always going to be some uncertainty because there's limited precision with the measurements and tools that we're using. So again, there's exact numbers, but then there's also numbers that have uncertainty. And that's what we're focusing on in this PowerPoint here. So those are our measurements or our measured numbers. So whenever we take a measurement, we represent that measurement with what's called significant digits. So we record all the numbers that we're certain of, and then we have the last digit at the end of that that's considered an estimate. So something that we're not certain of. So for example, if I recorded this pencil length here as 4.72 centimeters, I'm certain of the 4.7, so I'm certain of that 0.7 there because it goes up to the 0.7 over here. But if I just wrote 4.72, well, scientists would know that, okay, there's some uncertainty here. It's 4.72 plus or minus 0.01, so it might be 4.73 maybe. So it's kind of like saying 4.72 give or take a few, because you're expressing there that there's some uncertainty in your measurement, and there's always going to be uncertainty in measurements when it comes to science. So what we need to do is be able to count the number of significant digits there are in numbers and measurements that we see. So there are some rules for determining what type of digits are considered significant digits, and you need to go over those rules to make sure that you could accurately report how many significant digits you have in a certain measurement. So the first rule is that all digits 1 to 9, so basically these are non-zero digits, 1 to 9, are considered significant. So let's say you had the number 129. Well, what that means is you have one sig fig here, one sig fig here, one sig fig here. You might also hear us say significant digit or significant figure, or you could say sig dig as well. Okay. Another rule is that zeros in between digits are considered significant as well. So look at the number 2008. We have digit 2, digit 8, and in between there are zeros, so that makes these zeros significant as well. So this number here has 1, 2, 3, 4 significant digits. Basically, there's some uncertainty in this last digit over here. It could be 2009. It could be 2007. So there's uncertainty in that last digit. Okay. Now, trailing zeros without a decimal, they're considered not significant. So if we look at 2000, the 2 is significant because it's a non-zero digit. And since there's no decimal afterwards, these other zeros here, they're not considered significant digits. So there's only one significant digit in this particular measured number here. Now, let's look at the number 2000.0. If you have trailing zeros, so zeros that basically come after something, come after a number, basically that will be considered significant if there is a decimal in place. So we have 2000.0. Because there's a decimal here, these zeros have now become significant. So now we have 1, 2, 3, 4, 5 significant digits, whereas something like 2000 only had one significant digit. Leading zeros, so zeros that come before something, they're considered not significant. So 0.0035, this just has 3 significant digits. Because these zeros here in the front, they're just placeholders. They're telling you that you have a decimal, 0.0035. So they're not significant, only 2 significant digits. Let's say you had, for example, 0.00005. This only has 1 significant digit because these leading zeros, these here are leading zeros. Let's say you had 0.0050. Now, what you're saying here is that you have a bit more precision in your measurement. There's 2 significant digits here. There's the 5 and the 0. Now, I know it's trailing, but it's after a decimal. Here, these are not trailing, these are leading. This is trailing after a decimal, so that one's considered significant. So this one here has 1 significant digit, this has 2 significant digits. So what this measurement implies here is that, you know what? You know that it's 0.005, but it could be 0.06, 0.04 maybe. So there's uncertainty in this digit over here. Over here, you're a bit more precise. You know for sure that it's 0.005. You're just a bit unsure about that last digit here. It could be 0.0051, 0.0 maybe 52. So you're a bit unsure there in that last digit. And lastly, the last rule you need to know here is that all digits in the scientific notation are considered significant. If you haven't learned scientific notation yet, you will learn it eventually. But basically, this is a format that you can use to write large numbers in or small numbers in. And it's a way to allow us to express these numbers more efficiently, but also to be certain about what digits we want to be considered significant. So, for example, over here, you have 1, 2, 3, 4 significant digits. Don't count this here. I mean, it is part of the number, but it's not considered the significant part. It's really this part here is considered the significant digit. I'll just give you another example. So let me go back to 2000 here. When you write 2000 like this, this means that you only have 1 significant digit because the zeros here are trailing. And there's no decimal point either, so there's only 1 significant digit. Now, sometimes this is a bit ambiguous or confusing. Some people might actually want all of these zeros to be significant. They might actually have some precise measurement. And there's a few ways you can actually make all of these zeros here significant. You can do this, 2000 point, and just put a point. And that means that all of them are significant. So you're saying that, you know what, I know it's at least 2000, but I don't know what the last digit here is. It 2001? So this would make it have 4 significant digits. Another way to make all these digits significant, if you wanted that, is to make it in scientific notation. So you put 2.000 times 10 to the power of 3. And so all of these now are considered significant digits. So like I said, sometimes this case is a bit ambiguous or confusing. With the rules I taught you and that you're learning this year, we're going to go with that there's only one significant digit, but some scientists might actually mean to say that there's more than one significant digit here, because maybe we do know that it's at least 2000 and there's just some uncertainty here. So to make that more clear, again, you can just put the dot or make the scientific notation form. And again, you'll learn the scientific notation form a little bit later on. So now you can attempt these problems here. You have to identify how many significant figures there are in the numbers provided. So you should pause the video, try it out yourself, and then afterwards come back and take a look to see if you are on the right track. So I'm going to write the answers out, and you can verify your answers as we go throughout. So 235, these are all non-zero digits, digits 1 to 9. So there's 3 significant digits. 30.00, you have a decimal place. Because you have a decimal place, these zeros have become significant, especially since they're after a non-zero digit. So here we have 4 significant figures. We're really uncertain about this last digit here. Here we're uncertain about this last digit over here. 90,000, no decimal place. Only one non-zero digit. Trailing zeros here are non-significant, so 1. One significant digit. So basically we're unsure about that 9 there. It could be an 8. It could be something other than 9 because we're unsure. Our measurement tool is not precise enough. Here, the non-zero digits, or the 0 digits, the leading ones, are non-significant, but zeros to the right of non-zero digits in the decimal place are considered significant. So here we have the 5 and the 0, so we have 2 significant digits. Here we have 2 non-zero digits and a trailing 0 with no decimal. The trailing 0 with no decimal is considered non-significant. So we're really unsure about this 3 here. It could be 24, it could be 22, we're not sure. It could be 230, it could be 240, it could be 220, we're not sure about that. So this has 2 significant digits. And here we have the scientific notation form, where all the digits within it are considered significant. So all these over here are considered significant. So we have 1, 2, 3, 4, 5 significant digits. So our first step is being able to identify significant digits. Now we're going to take a look at operations using significant digits. So when I say operations, it means like adding. It means things like adding, dividing, multiplying, subtracting. And this will allow you to understand when and why we decide to round to a certain number of decimal places. It's really following the rules of significant digits. So when you want to do addition and subtraction with significant digits, what you want to do is you want to make sure your final answer is rounded to the amount of significant digits, or rather to the amount of decimal places that the number in your addition or subtraction had the fewest of. So for example, if we look at 2.5, there's 1 decimal place here, but there's 2 decimal places here. So what that means is our final answer needs to be rounded to 1 decimal place. And the main reason that is because your final answer can't be more precise than the measurements that led to it. You can't have a very unprecise measurement and all of a sudden say you have a super precise answer. It just doesn't make sense. So your answer cannot be more precise than the measurements that led to that answer. So here, for example, we have 2.5 plus 3.72 gives you 6.22. We have to round to one decimal place, so what that means is we're rounding to the tenths over here. Look next door, that's less than 5, so it becomes 6.2. Don't put 6.20, remember we're rounding to one decimal place in this case. So now let's try this one out. So you can pause the video, try it yourself. You can do it in your calculator and then round to a proper number of decimal places. So when I put this in my calculator, I get 95.878. Now let's see which one has the fewest number of decimal places. This has 2, this has 1, this has 3. So we're going to round to one decimal place because this is the fewest number of decimal places. So we want to the tenths. Let's look next door, higher than 5. So we get 95.9. There are also rules with multiplication and division. Count the number of significant figures. So for multiplication and division, you want to make sure that your answer has the same number of significant figures that the number with the least number of significant figures had in your actual operation itself. So for example, if we look here, 2.6 times 1.35, 2.6 had 2 sig figs, whereas 1.35 has 3. So our final answer should have 2 significant digits in it. 2 significant digits, or 2 SFs for sig figs. So we have 3.497, that's what you'd get if you put that in your calculator. And we want 2 sig figs, so that basically means our 3 is 1, and then some other significant figure over here. So we're rounding to the tenths to get 2 significant figures. So you basically just look next door, and you get 3.5. So let's try this here. Here we have 900 divided by 1.345. We have trailing zeros and 1 non-zero digit. So this is 1 significant digit here. And here we have 4 significant digits. So our final answer is going to be 1 significant digit. So we have to do our 900 divided by 1.345, and we get 669.149,814. I'm just putting all my digits down just to show you what I got in the calculator. Now we want 1 significant digit. So basically, we want to round to the nearest 100. So we look next door, higher than 5, so this is going to be 700. Don't put a decimal because we want these trailing zeros to be non-significant. So we have 700 as our final answer in this case here. Now sometimes you'll have mixed calculations where you have some addition, multiplication, division, subtraction. Go with the rules where you're counting the number of sig figs. So you want to have the least number of sig figs in your final answer. So if you take a look here, we have 2.6 times 1.35 plus 3.34. Remember, when you're doing math, you want to do what's in brackets first, right? Remember BEDMAS, brackets first, followed by exponents, followed by division, multiplication, addition, and subtraction. So the least number of sig figs here would be 1 significant digit. And as you can see, when you put this in your calculator, you get 6.85. But since you want 2 significant digits rather, 2 significant digits. Since you want 2 significant digits, you have to, your non-zero digit is considered significant, so you want to round to the 10th. Look next door. Now, since you look next door here, the reason that this was actually rounded to 6.9 is because in your calculator, you would have obtained 6.85 something something something. So something's following this 5 here, and that's why we decide to round up to 6.9. Remember that when you have 5 followed by non-zero digits, you're actually going to round that number next to it. Let's try this one here together. So you can actually pause the video, try it yourself, and afterwards we will check the answer. So you can put it in your calculator. You can do the 2.45 plus 6.789. And I know that that's an addition, but we're doing it first because it's in brackets, and you want to do the brackets first. That's the rule here. Once you do that, you can multiply it by 3.33, and we get 30.76587. Let's go take a look at which one had the fewest number of significant figures. Well, there's two that had the fewest number of significant figures. It was a 2.45, a 3.33. This one had 4 sig figs. So we don't want 4 sig figs. We want to have 3 significant figures or significant digits. So our 3, 0, they will be significant. I know there's a 0 there, but it's in between non-zero digits, and it's also before a decimal here. So we want to have this rounded to the tenths to get 3 significant digits. So look next door, and that's going to go up. So we're going to have 30.8 as our rounded answer. And that's how you know what to round to when you're doing calculations. So now that we've done the rules for significant figures in terms of how to identify the number of significant figures and how to do the operations for significant figures, you should be in a better position to actually do the significant figure problems found within the numeracy booklet. The videos that were posted in the first slide are a great resource that you should watch in order to become more effective at identifying sig figs and at doing operations with significant figures or significant digits as well. One more little caveat or little trick to mention. If you are dealing with an exact number, don't count that in your number of sig figs for operations. So for example, let's say I measured 20.2 and I want to divide that between 2 people. That's a counted number. It's an exact number. So there's no significant figures in there's infinite significant figures, I should say, rather, in a counted number, meaning it's so precise that there's as many significant figures as we need it to have. So that's why you don't want to count this exact number here in your count for significant figures. So if you know something is an exact number, so if I'm dividing into exactly 3 containers, if I'm dividing between exactly 3 people or 2 people, then in that case, you're not going to count that in your calculation. You're going to ignore that, and you're going to just kind of deal with the other figures to determine your number of sig figs in your final answer. So here we have 20.2 split between 2 people. We're going to have 3 significant figures in our final answer, not 1, because this is an exact number over here. Okay, so just think carefully when you're doing problems like that. If you see there's an exact number, don't count that in your significant figure because they have infinite numbers, an infinite number of significant figures if you're an exact number.